So absolute value inequalities are an extension of compound inequalities, which is what we talked about on Friday in our last lesson. So an absolute value inequality is essentially either going to be an and or an or problem. So an absolute value inequality is an or if your absolute value is great or then its value. It will be an and if the absolute value is less than the inequality. So in that first example, we have the absolute value of 2x minus 5. And if you read that, it's the absolute value of 2x minus 5 is greater than 3. So that tells me that this is an or inequality, which means that when I write this, I'm going to say that the absolute value of 2x minus 3 becomes 2x minus 5 is greater than 3, or 2x minus 5, change the direction of the inequality, is less than, and just like our other absolute values when we were solving with equals, it's the opposite of the other side. So it will be less than negative 3. So now the absolute value inequality became two inequalities. These are or inequalities, so our solutions will probably go in opposite directions. They're both open circles, so I'm going to solve for x in each case. So I get x is greater than 4 or x is less than 1. Open circle at 4, shade to the right. Open circle at 1, shade to the left. So that means I could plug in any number over here and any number over here, and they would make that absolute value inequality true. So like 2 times 0 minus 5 inside the absolute value becomes the absolute value of negative 5, which is 5, which is in fact greater than 3. So if you had time and you wanted to check it, you could simply plug it in and test your points. That is not mandatory or part of the homework for this lesson. There are no extraneous solutions for absolute value inequalities like there were for absolute values. Okay, number 9. The absolute value of 2x minus 3 is greater than 7. So 2x minus 3 is greater than 7, or 2x minus 3 is less than negative 7. Solve for x on both sides. So you get x is greater than 5, or x is less than negative 2. So open at negative 2, open at 5, and again, it's an or, so they're going in opposite directions. So my solutions are less than negative 2 and greater than 5. Okay, in the next two examples, just like in the previous examples, you must isolate the absolute value before you split the problem. So we have to isolate the absolute values. So I'm going to subtract 5. Divide by -2. And the rule still applies. If you divide by a negative, the absolute value doesn't change, but the direction of the inequality does. So it's the absolute value of x plus 1. Now it's less than 4. So this becomes an and problem. So it's x plus 1 is less than or equal to 4, and x plus 1 is greater than or equal to -4. So x is less than or equal to 3, and x is greater than or equal to -5. So my solutions live between them. So close circle at -5, close circle at +3, shade between. In 11, we're going to do the same thing. We're going to isolate the absolute value by adding 7 to both sides. So we have the absolute value of 5z plus 3 is less than 41. So this is an and. So you have 5z plus 3 is less than 41, and 5z plus 3 is greater than -41. Subtract 3 from both. Divide by 5. So you have z is less than 7.6, but greater than -8.8. So on your number line, you have open circles at -8.8 and open circle at 7.6 and shade between. All right, so we're actually going to skip this entirely. I've removed it from, it's been removed from like the SATs. So that was one of the reasons I put it out there. So we're not going to look at it. So your homework, which you have not tons of time, but like almost 15 minutes to start, is the next pages in your packet. So you're doing 16 to 22. All right.